All right, let's jump right in. We're going to talk about something that sounds, well, complicated. Complex numbers. But here's the secret. What if they aren't about complicated algebra at all? What if it's all just simple geometry? Stick with me, and I promise you're going to see these numbers in a completely new light. So, let's start with a really big what if. What if that name, imaginary numbers, has been misleading us all along? What if these numbers aren't imaginary at all, but are actually describing something incredibly real? Something like rotation. Just chew on that idea for a second as we get started.
To really get this, we've got to break free from how we usually think about numbers. We're all used to the number line, right? That one flat dimension stretching left and right. Well, complex numbers are basically an invitation to step off that line and into a whole new dimension.
So at its heart, a complex number, which we write as z equals a plus ib, is really just a pair of normal, everyday real numbers. We call a the real part and b the imaginary part. And that little I? For right now, just think of it as a kind of label that keeps a and b separate. Okay, so if a complex number is just a pair of numbers, where do we actually put it? Well, on a map. A two-dimensional map we call the complex plane. The horizontal axis is just our good old number line. That's the real axis for the A part. And the vertical axis? That's the imaginary axis for the B part. So every single complex number isn't some abstract formula. It's a location, a point on a grid with coordinates A, comma B. So now we know what they are and where they live on our map. But what happens when we try to, do math with them? This is where things start to get a little mysterious. Okay, check this out. When you add complex numbers, it's exactly what you'd expect. You add the real bits, you add the imaginary bits. Simple, clean, intuitive. But then you look at multiplication, and it's just this mess. I mean, where on earth does AC minus BD come from? It feels totally random, right? Like someone just pulled this complicated rule out of a hat. And that, right there, is the big question for today. What is this crazy-looking formula actually doing? Is it just some arbitrary rule we have to memorize for a test, or is there something deeper, something more intuitive, hiding underneath all that algebra? Well, here's where we pull back the curtain and find the secret. To make sense of that messy formula, we have to stop thinking like algebra students and start thinking like geometers. We need to shift our whole perspective from how it works to why it works. And this is it. This is the big idea. When you multiply by a complex number, you're not just doing a calculation. You're issuing a command. It's a two-part instruction to do two very simple things: scale and rotate. Let me break it down. It's a two-step process. First, you scale. You take the number's distance from the center of the map and you stretch or shrink it. Second, you rotate. You swing that number around the center by a certain angle. That's it. Scale and rotate. So you can actually picture it happening. It's a physical transformation. You're literally grabbing a point on the plane, stretching its distance from the center, and then swinging it around an arc to land in a new spot. It's not abstract math, it's movement. Okay, this is a huge breakthrough. If multiplication is really just about scaling and rotating, then our standard A plus IB way of writing things starts to feel a little clumsy. It's designed to talk about how far right and how far up, not how far out and what angle. We need a new language, a notation that's built for this geometric point of view. And here it is. It's called the exponential form. Now, I know it looks a little intimidating at first, but what it does is incredibly simple. That r right there, that's just the magnitude, our scaling factor. And theta, that's the angle, our rotation. This whole thing is built on top of Euler's famous formula, which is what connected these exponential functions to circles and rotations in the first place. It lets us speak the language of geometry directly. And this is the moment it all clicks. This is the payoff. On the left, you've got that algebraic monster we've been wrestling with. But on the right, that's the exact same operation, just written in our new geometric language. And look at it. It's beautiful. All you do is multiply the lengths and add the angles. That simple, elegant rule was hiding inside that complicated formula the whole time. So the rules were simple all along. To multiply two of these numbers, you just multiply their lengths and add their angles. Once you find the right way to look at it, complex multiplication isn't just easy, it's totally intuitive. Now, this new way of thinking isn't just pretty, it is seriously powerful. It gives us what feels like mathematical superpowers. It lets us solve problems that would be an absolute nightmare if we only stuck with the old algebra. For example, it leads us straight to this incredible shortcut called de Moivre's theorem. Think about it. Raising something to a power is just multiplying it by itself over and over again. So if multiplying means adding the angles, then raising to the nth power just means multiplying the angle by n. It's that simple. Let's put this superpower to the test. Let's say I asked you to find the fifth roots of the number 32. Now, algebraically, that is a really tough problem. But with our new geometric toolkit, it becomes surprisingly straightforward.
So, how do we do it? First, we put 32 on our complex map. Its length is 32 and its angle is 0. But wait, an angle of 0 is the same as a full rotation, 2 pi, or 2 full rotations, 4 pi, and so on. We can use all those angles. So we take the fifth root of the length. The fifth root of 32 is 2. Then we just divide all those possible angles by 5. And because we used multiple angles to start with, we don't just find one root, we find all 5 of them, just like that. And here's the absolute best part. When you plot those 5 answers on the map, they're not just scattered around randomly. No way. They form a perfect, beautiful, symmetrical pentagon. What started as a gnarly algebra problem has literally blossomed into a geometric shape. So let's circle all the way back to that clunky formula from the beginning. It turns out it wasn't wrong, and it wasn't arbitrary. It was just a shadow. It was the complicated shadow cast by a simple, elegant action, rotation, when viewed from the wrong angle. And really, that's the big takeaway from all of this. Finding the right perspective can change everything. By just shifting how we looked at the problem, from algebra to geometry, we turned something that was complicated and ugly into something that was simple, powerful, and honestly, beautiful. So, I'll leave you with this final thought. We started with a simple, one-dimensional line. We added just one more dimension, and this whole hidden universe of rotation and geometry suddenly appeared. It really makes you wonder, doesn't it? What other amazing patterns are out there, hiding in plain sight, just waiting for us to find the right perspective? Thanks for coming along for this one.